Welcome to the Explainer. Today, we're tackling something every hardware engineer faces. We're setting out to bridge that massive, often frustrating gap between theoretical math and actual functional hardware. We are going to completely demystify the common emitter amplifier. So let's just jump right in and turn some equations into reality.
Now, you might be asking yourself, why do we even care about this specific circuit? Well, think about the physical world. It's incredibly noisy, and the physical signals we actually want to measure, like a faint human heartbeat or a distant radio wave, are just incredibly weak. But on the flip side, we have our smart digital processors, and those digital brains, they need robust, crystal-clear voltage levels to do their computing. That is exactly where the common emitter, or CE amplifier, comes in. It's the ultimate high-gain bridge between these two completely different worlds. It's not just a random collection of resistors and capacitors, it's the foundational building block that translates raw reality into digital understanding. So, here's our game plan for today. We'll start with the core system bridge, then move into designing the DC bias. After that, we'll hit the small signal gain model, navigate through frequency response, and wrap everything up with some real-world lab troubleshooting. All right, let's kick things off with Section 1, the core system bridge, and meet the 2N2222A. This little component is the 2N2222A BJT. It's an absolute classic NPN silicon transistor, and frankly, it is the beating heart of our entire design. Literally everything we calculate, simulate, and eventually build today revolves around the physical quirks of this tiny three-legged piece of silicon. But we can't just plug it in and hope for the best. These components have strict physical limits that we have to respect. Take the absolute maximum collector-emitter voltage, or VCEO, for example. It's exactly 50 volts. If you push it past that, you permanently destroy the transistor. But even more crucially, we need to find its linear sweet spot. We want to keep it operating right where the DC current gain, the HFE, is nice and stable, somewhere between 50 and 300. Because if we let it drift too far and hit that saturation zone, our entire signal just gets completely crushed. Okay, moving right along to Section 2, designing the DC bias. This is where we set our blueprint constraints. You can really think of DC biasing a lot like pouring the concrete foundation of a house before you even think about putting up the walls. There's a logical, four-step process to hit our specs. First up, we decide on our operating current. Second, we figure out exactly how to allocate the voltage drops across the circuit. Third, we make absolutely sure the emitter is thermally stable. And fourth, we design the resistor network at the base to lock everything solidly in place. Let's walk through how this actually plays out mathematically. Say our goal is a 12-volt supply with a gain of at least 40 decibels. For step 1, we'll set our collector current, our IC, right at 1 milliamp. That gives us a really nice balance of power and linearity. Step 2, we want our AC signal to have maximum headroom to swing up and down without clipping, so we allocate exactly half of our 12-volt supply right to the collector, making VC 6 volts. Now that we have our current and our voltage, we can easily calculate our collector resistor at 6 kiloohms. Then, we just follow that logic straight through to emitter stability, bringing us to step 4. We set a 3-to-1 ratio for our base resistors, which mathematically shakes out to 150 kiloohms and 50 kiloohms. As you can see, the math directly dictates the hardware. If you take one thing away from this, let it be this golden heuristic. Always check your DCQ point first. Seriously, before you ever inject an AC signal into the mix, before you even think about looking at a frequency plot, you have to verify that your DC voltages actually match your blueprint. Because if your foundation is cracked, your amplifier is practically guaranteed to fail. Make sense? Great. Let's head into Section 3, the small signal gain model, where we translate reality into math. This is where things get really interesting. To analyze AC signals, engineers use what's called a pi model equivalent. We're essentially taking the messy, complex physics of a physical schematic and swapping it out for a clean, simplified mathematical model. It gives us an input resistance and, most importantly, a dependent current source right smack in the middle of the circuit. Now, that dependent current source, it's completely driven by a property known as transconductance, which we call GM. You can think of transconductance simply as the actual engine of the amplifier. It strictly dictates exactly how effectively a minuscule flutter in our input voltage gets scaled up into a massive, powerful swing in our output current. And here is where all that math finally pays off. When you look at the core gain formula, our voltage gain is just negative transconductance multiplied by the parallel combo of our collector and load resistors. So when we plug our DC blueprint numbers into this AC formula, we get a theoretical magnification of 148 times. That translates to roughly 43.44 decibels. Remember how our initial design constraint was 40 dB? Yeah, we completely smashed that target.
Let's keep the momentum going with Section 4, Navigating Frequency Response. Consider this our virtual stress test. As we test how this circuit handles different signal speeds, from a slow, rumbling 10 Hz wave all the way up to a screaming 10 MHz signal, you're going to hear the phrase -3 dB cutoff frequency quite a bit. This is a universally agreed-upon magic threshold. It's the exact point where the amplifier's output is no longer considered effectively flat. It literally defines the boundaries of our usable bandwidth.
But what does a drop of -3 decibels actually mean in real life? Well, there are two ways to look at it. If you're looking at power, a 3 dB drop means the amplifier is outputting exactly half of its maximum power. Pretty straightforward. But from a voltage perspective, which we use way more in small signal design, it means the output voltage amplitude has dropped down to roughly 70.7% of its maximum midband value.
When you map this out on a Bode plot, it becomes incredibly clear. You'll see this wide, flat plateau right in the middle. That is our midband. In that specific frequency range, our amplifier is effortlessly delivering that full 148 times magnification without breaking a sweat. But at either end of that plateau, notice how the curve just drops off a cliff? Those drop-off points are our lower and upper -3 dB cutoff frequencies.
So what's actually causing those cliffs? Well, on the low frequency end, the culprits are the external capacitors. The coupling and bypass caps basically act like a brick wall to slow-moving signals because their impedance shoots through the roof. But the high-frequency ceiling, that one's a lot more insidious. That is the Miller effect. You see, there are these tiny, unavoidable parasitic capacitances baked right into the physical silicon. And they get multiplied by the amplifier's own high gain, effectively creating a massive phantom capacitor at the input that just swallows high-speed signals whole. Wild, right? All right, final stretch. Section 5, Real-World Lab Troubleshooting, where we actually build the circuit. When you finally hook your physical, real-world circuit up to an oscilloscope, there are specific signatures you need to hunt for. Ideally, you want to see perfect, clean sine waves. That's perfect linear gain. But if you see symmetric clipping, where both the top and the bottom of the wave are just chopped off flat, it simply means your input signal is way too loud for the empty handle. However, if you're getting asymmetric distortion, say only the top is flattened or only the bottom, that points to a much deeper underlying issue. When you actually see those distortion signatures on a scope, it tells a very specific story. If the top of your wave is cleanly sliced off, your Q point is sitting way too high and the signal is literally crashing into the 12-volt ceiling. If the bottom is getting sliced off, your Q point is too low, forcing the transistor down into saturation where it just can't turn off any further. This visual feedback is incredible because it tells you exactly which DC bias resistor you need to go in and fix. And fixing it usually means diving headfirst into the breadboard. Now, breadboards are an absolutely fantastic canvas for prototyping, but let's be real, the wiring can quickly turn into a chaotic nest of metal. And in the real world, every single one of those looping wires acts like a tiny antenna. They pick up stray electromagnetic noise, sometimes even the local top 40 radio station, and inject parasitic resistance and capacitance that your nice, clean mathematical pi model never accounted for. To fight off that physical chaos, there are 3 strict rules you absolutely have to follow in the lab. Rule 1, isolate your power rails. Never let your delicate signal lines share the same physical tracks as your power or ground. Rule 2, give your BJT pins some breathing room. Don't crowd your passive components right on top of the transistor, or you're begging for thermal issues and shorts. And Rule 3, keep your signal paths as short as physically possible. That minimizes those antenna effects and keeps the high-frequency noise at bay. So, we've covered a ton of ground today, from the absolute limits of a tiny piece of silicon, through the rigorous logic of DC biasing, and all the way past the invisible hurdles of the Miller effect. You've seen exactly how to build a robust, high-gain bridge between the physical and digital worlds. You've got the blueprint, you've got the math, and you've got the lab heuristics. So, the only question left to ask is, what will you build with your common emitter amplifier? Thanks so much for hanging out with me today, and I'll catch you in the next explainer.